This is an outline of the operation of the HP8970 Companion, an open-source Linux program to augment the functionality of the HP8970 noise figure meter. The 8970A noise figure meter was introduced by Hewlett Packard in 1983 in order to simply and accurately measure device noise figure. Its user interface is rather Spartan by modern standards. However, its underlying measurement capability is very good, and the instrument is still a useful addition to a 21st century RF electronics lab. The 8970 is connected to a modern computer using its HPIB interface, now commonly referred to as GPIB or sometimes IEEE 488. The program I will describe uses this interface to control the 8970 and to obtain its measurement data, giving the user a modern interface and adding a graphical display, storage, and printing capability. Noise figure is a measure of how much a device, such as an amplifier, degrades the signal-to-noise ratio. It is the ratio of signal to thermal noise at the input to signal-to-noise measured at the output of the device. Let us briefly examine the user interface and how the program controls and receives data from the 8970. Pressing the sweep button with a left mouse button click will trigger a single sweep, measuring noise figure and gain at frequency increments defined by the step frequency sweep setting. If the sweep button is pressed with the right mouse button, the button acts as a toggle and the 8970 will sweep continuously, overwriting previous sweep measurements until the toggle button is turned off. Pressing the Calibrate button with a left mouse button click will trigger calibration sweeps at frequency increments set by the step frequency calibrate setting. Pressing the Calibrate button with a right mouse button click will trigger a frequency calibration, which takes about a second or two and recalibrates the Yig-tuned oscillator. Pressing the Spot toggle button will initiate the continuous acquisition of measurements at the defined spot frequency. The period between measurements increases with smoothing factor, as the 8970 accomplishes this by averaging the defined number of measurements. The scrolling display will show the time capture on the ordinate axis. This display is useful in showing long-term drift in gain and noise figure, or to determine when the system has stabilized after power-up. Checking the correction checkbox will set this control on the 8970, which will then report noise figure and gain, correcting for the noise figure of the instrument. This will only work if the instrument has been calibrated at the measurement frequency. The next set of buttons are used to print the displayed plot to a system printer, or to save the image in either PDF, SVG, or PNG format. The plot data may also be saved as a CSV text file. The button with the camera icon is used to copy the measurement data to a memory trace, permitting the display of the memory trace and the measurement trace simultaneously, a useful feature when tuning a device under test or when comparing current to historical performance. The last two buttons on this row are used to save and retrieve in JSON format the trace and the instrument settings at the time of measurement. When moving the cursor over the active area of a noise figure or gain trace, a live marker appears and the corresponding frequency, noise figure and gain displayed. In this way, data may be intuitively interrogated. The marker may be held at the current cursor location by pressing the left mouse button and released by pressing the right mouse button. The measurements shown on a held live marker may be printed or saved to an image. The Notebook widget in the lower left of the graphical user interface holds 7 pages. The first of these, labeled Special Functions, holds some of the controls that the 8970 documentation describes as thus. It also includes widgets for the saving and recall of named configuration setups. The Notebook page labeled Notes is used as an aide-memoire and is saved and recalled with the JSON format file. A user may wish to describe the test conditions, equipment, or anything else. The Plot page contains controls to manually set the coordinate scaling or to enable auto-scaling. This page also contains widgets permitting the user to customize the color of plot elements. The External Mixer page is used to configure an external signal generator for its use in down-converting microwave frequency signals in modes 1.1 through 1.4. The user enters the GPIB or SCPI setup and frequency setting strings appropriate to the particular signal generator used. The format of the set frequency string is that of the C programming language printf. In the example shown, %.0LF formats the double representation of the frequency in megahertz as a number with no fractional component. The modes used for microwave frequencies have either a fixed LO frequency or a fixed IF frequency. The selected sideband will affect the LO frequency or IF frequency the program calculates. The range of LO frequencies that the external generator is swept, or the down-converted frequency range, where appropriate, is displayed at the bottom of the Notebook page, along with the frequency range of the image that must be filtered out. The Options page contains widgets to set the size of the PDF and SVG images and to permit the user to display or hide some peripheral plot elements. The Radio button set at the bottom of the page is used to set the 8970 variant. The A model has 81 calibration points and the B model 181. The maximum frequency of all 3 variants is different, so setting this control slightly modifies the behavior of the program. For example, the program warns the user and disables the Calibrate button when the chosen step size for calibration is inappropriate for the frequency range. The Source page is used to edit and upload the ENR versus frequency table for up to 5 noise sources, for those fortunate enough to have more than one. The entries may be edited and saved, or uploaded to the 8970 without being saved. The GPIB page is used to configure the address of the 8970 on the HPIB and that of the external signal generator for modes 1.1 through 1.4. The user may use the primary ID and controller index directly, or use the label defined in the Linux GPIB configuration file. Calibration is used to determine the noise figure of the test system so that it can be accounted for when determining the noise figure of the device under test. When operated in mode 1.0, the 8970 system is calibrated by connecting the noise source directly to the input, setting the start and stop frequencies, smoothing factor, step size for calibration, and pressing the Calibrate button. Calibration is performed at 3 input gain or attenuation levels. During calibration, the display shows the noise figure of the measurement apparatus at that gain. On completion, the controls become active again and the corrected noise figure measurements can be performed within the frequency range. There is a limited number of calibration points, 81 for the A model and 181 for the B model. If the combination of step size and sweep frequency range results in more calibration points that are possible, the step frequency display color will change to red and the Calibrate button will be desensitized. In this eventuality, increase the step size or adjust the sweep frequency range so that the number of calibration points is equal to or less than the maximum for your 8970 model. A single measurement sweep is initiated by activating the sweep button with a left mouse button press and continuous sweeps with a right mouse button press. Most controls are disabled while the sweep is in progress. To interrupt a sweep, press the escape key on the keyboard. The 8970 will sweep from the start frequency to the stop frequency, stepping up by the step frequency sweep setting. Several measurements may be made at each frequency and averaged to effect smoothing. This will slow the scan but improve accuracy. The plot being shown now averages 32 samples per frequency and is speeded up by a factor of 4. If set to auto scale, the plot will rescale when necessary based on newly acquired data. If a static fixed scale is preferred, disable auto scale and set the coordinate scale bound on the notebook plot page. If the memory trace is shown, the auto scale settings use data from both the memory and the measurement traces in setting scale boundaries. Noise factor and gain at a single frequency can be continually measured and displayed on a plot with time rather than frequency as the ordinate axis. Set the spot frequency and smoothing factor and press the spot button. The time span shown on the plot scales with the smoothing factor. If a long period is to be shown on the plot, choose a high smoothing factor. Conversely, a smoothing factor of 1 will result in a plot spanning 1 minute. The measurement trace may be stored in a memory trace and both the historic and current data plotted together. This permits the user to see the difference between the current device noise figure and gain and a baseline. This is quite useful when tuning a device or when testing for deviation over temperature, voltage or time. To create a memory trace, first load a previously saved plot or capture a new one. Press the memory button, which is the button with a camera icon, to transfer the measurement trace to the memory trace. The memory trace is shown with a dotted line, but will be obscured by the measurement trace if they are identical. The memory trace may be hidden by disabling the checkbox on the Notebook Options page. The memory trace is deleted by using the right mouse button to click the memory button. The native frequency range of the 8970 is from 10 MHz to either 1500, 1600 or 2047 MHz, depending upon the model and options. The instrument can measure noise figure of devices at microwave frequencies by employing the use of an external mixer and local oscillator, as shown in the diagram. Indeed, the 8970 can act as a GPIB controller to control an external signal generator. This approach, however, has several serious limitations. The length of the custom command strings is very limited. There are very few predefined older HP signal generators, and at least for the A model, no other GPIB controller can communicate with the 8970 at the same time. The 8970 Companion solves this by taking the burden of controlling the external oscillator from the instrument. The user defines a setup string that is sent to the signal generator to configure it, and a string to change its frequency. The settling time of the signal generator is defined to ensure the signal is stable before a measurement is triggered. The simplified diagram shown in the 8970 pull-out cards will work, but I have found that most mixers will present a poor return loss to the device under test, resulting in measurement errors. In my experience, this presents itself as a ripple in the noise figure and gain over the frequency sweep. The problem is corrected by adding an isolator or attenuator before the mixer to present a good load to the device under test. Additionally, depending upon the gain or loss of the device under test, it may be advisable to add a broadband amplifier to overcome losses in the frequency conversion system. There are several hotkeys to find that the user will find helpful. To prematurely terminate a calibration or sweep, press the Escape keyboard key. This will terminate the program's GPIB read or write operation, but the instrument itself may still be making a measurement. This is likely if, for example, a very high smoothing factor is set. In that case, pressing Shift Escape will instruct the GPIB controller to issue a GPIB clear that will make the 8970 become responsive immediately. The F1 key will display the Linux help system, which will provide details of all program functions. I would like to thank and acknowledge the help of Dave Penkler, who is the maintainer of the Linux GPIB driver, and Juan Pablo Ugarte, the author of the Kumbalachi GTK user interface maker. The program source code is available on GitHub at the address listed here. To install on Fedora Linux, simply run the commands shown. To build and install the program on other Linux distributions, use the AutoTools package. Instructions are given on the GitHub page. Thank you for your interest, and I hope you find the program useful.